So let's kind of pick up where we left off. We talked about discrete versus continuous random variables, and discrete versus continuous as a concept. We think of discrete things as being countable, as having nothing in between them, right? If we're counting 1, 2, 3, 4, if we're going to be discrete, we're not going to say 1.00000000001 or something like that. There's a little caveat in there. We can discretize by things that are not whole numbers, but for now, let's just think of it as being there's nothing in between two items that are in numerical order in a discretized understanding. And then continuous, we very often think of in terms of measurement, right? Where if we're thinking about the height of everybody in the world, if we have precise enough instruments, we're going to see that there are no two people who are the same height, or no two trees in the forest that are the same height, something to that effect. And one of the interesting things about this is we can discretize continuous outcomes or continuous values. The way we might do that is by creating buckets or bins. So maybe we say if a randomly generated value between 0 and 1 falls between 0 and 0.1, then we increment the count of values that falls between 0 and 0.1, right? That's actually how we get histograms, or a way that we can think about building histograms from continuous values. So defining a random variable, a random variable just represents the outcome of some experiment where we don't know what the outcome is going to be, right? And we can think of experiment as being something fairly loosely defined. I'm probably going to refer to experiments as phenomena. That's how I generally talk about it. And one of the keys here is that we define what that outcome is. We take the view of what that outcome is. And I gave a couple of examples of that yesterday. And I just want to give a couple more quick examples. So here we have a random variable x, which I've defined to mean it's the count of ones in a base 3 number of length 3. So if we're thinking about all of the potential outcomes here for base 3 of where the numbers are length 3, then if that random variable x is the count of ones, well, in this case, right, we can see that we can only have up to the value 3, as it turns out, right? We're not summing the values in here, right? So if I look at 222, well, 222 is actually 0, right? According to how we've defined our random variable x. Whereas 111 is 3. 112 is 2. Because there's 2 ones in there, right? So it's the count of ones in this definition. So that's a particular phenomenon, and we've defined the random variable to represent some facet of that phenomenon, right? And if we're building the sample space for that, then we get something that looks like this. This is kind of cool. It has a nice symmetry to it. I didn't know this beforehand, but yeah, if you look at this, it's kind of a cool pattern. So we can look at this. We can look at this sample space, and we can ask a question. And we would frame that question like this. What is the probability that x is 3? And looking at this, there's only one outcome where the definition of x leads to x being 3, and that's 111 here. Now, x doesn't represent these values up here. X represents these values, and that's important to remember. So that we put rules that generate x, and then we look at those outcomes for x, and we can think about a frequency histogram for this, right? We could count the zeros, we could count the ones, we can count the twos, and create some kind of representation of this space. And there's 1, 3 here, and that's an important way to think about this. Okay, So what is the probability that x will equal 3? Well, there's only one outcome where x equals 3. And there are 27 total outcomes. So the probability that x is 3 is that familiar cardinality of A over cardinality of S concept, cardinality of the subset over the cardinality of the containing set, and that's 1 over 27, right? Just 1 over 27. So we can define another random variable using the same phenomenon. And this is key. This is key to understanding how we think about random variables. So we can let the random variable y represent whether a 2 is present in a base 3 number of length 3. So y is 0 if there is no 2 present. Y is 1 if the 2 is present. So again, we have all the possible length 3 trinary outcomes, right, that we can see here. And here's the translation of that for, this should actually say y right here, corresponding values of y, not x. I didn't change that. In fact, let me just change that really fast since 23 discrete random variables. Oh, there it is. Just want to make sure that that is correct. There it is. And okay, so here are the potential values for y, right? Well, if there is no 2 present, then this is 0. If there's 3 2s present, then this is 1. Or if there's 2 2s present, it's 1. If there's 1 2 present, this is 1. So notice we have some kind of binary outcome for y. And we can ask this question, well, what is the probability that y will equal 1? Y equals 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 out of 27 times. And so we can just count that number of occurrences. Again, it's the subset A, the cardinality of A, or the cardinality of Y, right? The cardinality of Y equals 1, that is. It's the cardinality of Y over, the kind of magnitude of that space, of that sample space. So even though I didn't explicitly say this, that represents a probability mass function. So, we call these PMFs, and we'll make some distinction later between a PMF and a PDF. But a PMF is just, we call it a probability mass function. And it describes the probability that this discrete random variable is equal to a certain value. And we write that like this: the probability that big X equals little x, right? So big X here represents a set of values. Little x represents a specific value, right? And we can see that here, where we said the probability of y, what is the probability of that y equals 1? 1 here is like little y, right? So the probability that capital Y equals little y. And we can often clearly define a probability mass function in the sense that we will have some kind of closed formula for our known distributions, or we might, come across and be able to define a probability mass function for an unknown distribution, something that we invent. Or we can look at a bunch of outcomes, right, from, given a value of little x, or a range of values for x, between 0 and 1,000, we can look at the output of that, and then we can feed the input and output to a machine learning algorithm, and that machine learning algorithm can generate for us potentially a PMF if there's some good linearity here. Or at least, if not a PMF, some kind of model that works in place of a PMF, even if it's not complete, even if there's some kind of error in there as well. So along with the PMF, we also have the CDF. And the CDF is simple enough. It's just the probability that we get some value less than or equal to a specific value. So let me put this in kind of in a more concrete way. So let's think about just binary. maybe 3-bit binary, and I'll count in that. So 000, 001, 010, 011, 100, 101, 110, 111. We can make a histogram of these outcomes. And let's say we have a random variable, let's call it b, and b represents the sum of bits. So this is the sum of ones, right? The sum of ones. So here our sum of ones is 0. Here our sum of ones is 1. 1, 2, 1, 2, 2, 3. Okay, well that's fine. It turns out this is actually a binomial distribution, which we'll get to today in a bit. If I make a histogram of this, well, our potential values, our potential outcomes are 0, 1, 2, and 3. How many times does 0 occur? Well, it occurs 1 time, and I'm just going to do something like this. How many times does 1 occur? 1, 2, 3 times. 1, 2, 3 times. How many times does 2 occur? Well, that's 1, 2, 3 times. How many times does 3 occur? That occurs 1 time. Okay. So we've got this histogram. And I'm just going to make a copy of that. And now let's think about a cumulative density function for this. The way that we might think about this is, well, what is the probability that x, a random selection from this distribution, sorry, I called this b, let me call it b. What is the probability that b is less than or equal to, well, let's say 1? Okay. Well, we can count up all the instances where this is true. So less than or equal to 1, that's going to be this, and it's going to be this, right? And so we can see right there that the cardinality of the space where we're less than or equal to 1 is going to be 4, right? So this is just 4 over, what is that, 8, right? Which is 1/2 or 0.5. So we can see that the probability that b is less than or equal to 1 is 0.5. This is a cumulative function. And we're going to write cumulative density functions a bit later today. Well, maybe not today. We might get to it first thing tomorrow. Not tomorrow, Saturday. My apologies. First thing Saturday. Okay. Let me just close that. And okay, great. So I think that rounds out what we need to know about random variables. Just make sure. Oh, here's a little example that I put together, similar to the PMF example. Let the random variable represent the sum of ones in 4-bit binary. This is essentially the same thing I just did with B, except now we're dealing with 4-bit binary. And here are our corresponding values, and here's a histogram representing that. And we can ask the question, what is the probability z is less than or equal to 2? Well, we just count everything up here, add it to this, add it to this, and we get 11 out of 16. So we can see that. Now, we could define a different random variable here, right? We could ask, well, let's say the random variable c represents whether or not there are two 1 bits in a row, right? And then we have a binary outcome again. We have, this would be 0, this would be 0, this would be 0, this would be 1, 0, 0, 1, 1, right? And we could ask this question, well, what is the probability that c is 1? And that should be, well, if I just count this really quick, this is 1, 2, 3, 4, 5, 6, 7, 8, 8 out of 16. So it would be 0.5 in that case. And the probability that c would be 0 would also be 0.5. Okay. So let's take these ideas, the PMF, the random variable, the PMF, and the CDF, and apply it to the specific discrete distributions that we're going to be using. So that's under this. Okay. Now, this is a very long slide deck. We're probably not going to get through it today. And we're going to be, we might not, yeah, I'm just going to say that. We're not going to get through this one today. But we're going to be splitting our discrete distributions over a few days. So that's all right. What we're going to cover today is the idea of a discrete probability distribution. Essentially, we just did, but I'm going to touch on a couple other small facets of that. We're going to talk about the uniform distribution. Have that twice. A Bernoulli trial. And then we're going to seemingly sidestep a little bit and go on this binary tangent. And my reasoning for doing this is to give you a sort of fundamental understanding of where the binomial distribution comes from. And then when we talk about binomial, we're going to approach it in our 3 analytic approaches: counting, sampling, and using a closed formula. So the way we think about a probability distribution, right? We have this random variable that represents the potential outcome of a random experiment, right? And we can define that random variable through some set of rules. So we can apply different random variables to the same phenomenon. A probability distribution is just the frequency of occurrences of outcomes of a random variable. That's all that is. Probability distribution is just that. And we are going to talk about a small handful of these discrete probability distributions, really just 4 of them. We're going to talk about the uniform distribution. And this is simple enough. We've been doing this quite a bit, actually. If you roll a die and have equal outcome for any side of the die, that represents a uniform distribution between the lowest range of the die and the highest range of the die, right? So a 32-sided die or a 36-sided die those are going to have probability of any given side between either 1 over 32 or 1 over 36, respectively, to which die we roll. And then there's a Bernoulli trial. We've actually been doing these as well. If you flip a coin, that's a Bernoulli trial with probability of success. We define what success is. I'm going to assume it's just getting a heads. That's just the probability of 0.5. And there's only 2 outcomes, right? There's a simple binary outcome. Now, in the last set of slides, I showed you a couple problems that had binary outcomes, and the count of, let's say or whether or not you have 2 bits that are in a row, right, in 4-bit binary. That is a binary outcome. It's either no, you don't, or yes, you do, for any given outcome in that distribution of outcomes. So that's a Bernoulli trial, but underneath it is a series of Bernoulli trials, which we're going to get to that concept very shortly. So from Bernoulli trials, we can extrapolate out to the 3 other discrete distributions that we're going to talk about. Binomial distribution is the number of successes in a series of Bernoulli trials, where each trial has that same fixed probability, p, right? So the first trial, if the probability is 0.75, well, every other trial has to be 0.75. We can't have 0.75, then 0.3, then 0.29, right? All of those have to be 0.75, every trial in that series of Bernoulli trials. And then we have this Poisson distribution, which is going to feel different from binomial. But I'm going to try to tie it back into binomial when we talk about it. Essentially, if we understand that there is an average number of occurrences of an event in a certain span of time, let's say, 5 people walk by your front door during the hours of 1 and 3 p.m. On average, right? Let's say you live in a very, very sparse neighborhood. You can then extrapolate the probability that 7 people will walk by your door during that amount of time. you have to put some constraints on it. You have to decide that people will never be walking together, and you have to decide that no person walking is dependent on any other person walking or on themselves walking at a different time. You also have to decide that no matter when you look at this, the frequency of people walking, that average of people walking is going to be about the same. So when we approach the Poisson distribution, it's going to look a little strange. We're going to ask a question like, hey, 20 cars drive by this intersection in 5 minutes. What's the probability that 30 cars will drive by in 7 minutes? That's the kind of question that we're going to ask. So it seems like a very straightforward question, and there's some interesting things conceptually, philosophically about that. So the last distribution we're going to consider in discrete distributions is going to be the geometric distribution. And this looks a lot more like the binomial distribution. In this case, we're talking about the number of failures up to a success. So it's the distribution of failures up to the first success. Again, it's Bernoulli trials with a fixed value of the probability of success for any given Bernoulli trial. Okay. So talking about a uniform distribution, I already essentially said this. I think we can leave this here and move on to Bernoulli trials. So Bernoulli trial, simply stated, is just a single event with a binary outcome, and there's a set probability of success, right? So we talk about this in terms of, if we're thinking about it as zeros and ones, we talk about it as the probability of getting 1. And here's a simple version of this. If you have a bag of red and blue balls, where there are 30 red balls and 70 blue balls, and you reach in that bag 1,000 times, and average the counts of these balls, what percentage would you expect of those draws to be red, right? So what is the probability of red in this case? Yeah, 30 out of 100. And notice that the way I put this is like, well, we reach into this bag 1,000 times, right? So we're doing this over and over and over again. And what we would expect to see is 0.3 probability, or 30%, or 30 out of 100 times. Okay. So I'm going to have you code a Bernoulli function. And that function should take one argument, probability of success. You'll want to use this function from random import random. What that does is it returns a uniformly distributed random float between 0 and 1. Okay? So you're going to have a little bit of control flow in this. There's no for loop, nothing like that. You're going to draw from random and then decide whether to return 1 for success or 0 for failure. So let's put 4 minutes on the clock for that. And yeah, and go for it. If any of you want any more time on this, give me a thumbs up and I can add a couple minutes. All right, I'm going to go ahead and code a solution. So from random import random. And again, random is just going to return a float between 0 and 1. So we're calling this Bernoulli. And we have one parameter, the probability of success. And I'm defaulting that to 0.5, like coin flip, right? So I'm going to draw from this. And if that draw is less than the probability of success, then I can return true. And otherwise, I can return false. So let's see what that looks like. Let's talk about a probability of success of 0.3. Oh, you know what? I actually meant to put this in here. Okay. Let's run Bernoulli instead. So false, 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 true. You know, we can keep doing this all day. So let's verify this. It is working as we'd expect. Let's run this 1,000 times. So let's run it more than 1,000 times. Let's run it. How many do I have here? 10 million. Okay, well, let's do that. So I'm going to print Bernoulli. So I'm gonna do this in a comprehension. But all I'm doing is calling out to Bernoulli some massive number of times and building a list of that. So for whatever in range of the trials. And then after I do that, I can just count the trues in there and divide it by the number of trials, right? So that should give me the average. Oh, let's see. Is this correct? This is correct. Okay, that looks fine. That should give me something that approaches our expectation, right? So, or approaches our probability, that is. So I'll let that run for a little bit. 0.3000758. So it looks like that's working as expected. In the slide, I have a longhand of this, not in a comprehension, but essentially all this is doing is saying, well, for whatever in range trials, let's collect into a list Bernoulli with a success, a probability of success 0.3, and then at the end of that we count how many times true occurred, and we divide that by 10 million. Okay. So that's pretty straightforward, right? Bernoulli is pretty simple. It's just a coin flip. Maybe we have a fair coin and the probability is 0.5. Maybe it's an unfair coin and the probability is 0.9, right? Or maybe there's some other random variable that we define that has a binary outcome and a fixed probability, right? If that's the case, then it is a Bernoulli trial. Some people call it a Bernoulli distribution. I think that's fine too. It's just a distribution with two values, and we can think about it that way as well. So we're going to take the three analytic lenses on the binomial distribution: counting, sampling, and through a closed formula. We're going to start this off with counting, and the reason I like doing this is there's a historical reason for doing this. For one, Leibniz sort of came up with binary and was like, this is going to change everything, right? And then, hundreds of years later, it pretty much did. But I think of that history as informing where binomial comes from. I think there were a lot of things that, if you look at the history of the binomial distribution, there are a lot of things that where we have this emergent thing that we didn't really understand why, right? Sort of like the normal distribution. It's like you can observe these different outcomes for various experiments. But I think when you put it in the context of binary, in the context of counting in binary, things start really clicking under the hood. And I like this approach, and that's why I like to start with it. So how do we think about binary? Well, we've been talking about counting in different base systems and thinking about things as if they are numbers, different elements or different symbols in base systems. In this case, binary is just a two-symbol system. We've got a 0 and a 1. And so if we think about decimal in relation to binary, and I'm going to call decimal dec and binary bin, that's a very computer science-y way to represent it, and I'm just going to represent it like that. You'll probably see it like that in other places. We can make an association between a decimal value and a binary number, right? So in binary, the value 0, a single bit, as we'll call it, a single bit 0 is equivalent to the decimal 0, and a single bit 1 is equivalent to the decimal value 1. Well, that kind of just makes sense. What happens when we have 2 bits? Well, in this case, 00 translates to 0, 01 translates to 1. And then what we do is, and I know I've said this a number of times, but I'm just driving it home a little bit more. We flip this value, right? We flip this, let me make this just a little bit bigger, right? So we flip this 1 bit back over to 0, and because we do that, then we flip this 0 over to 1, right? And the maximum equivalent decimal value that we can represent in binary of 2 bits is the value 3, and we can see why, right? We can't actually store greater than the value 3. We can't represent greater than the value 3 in decimal in 2-bit binary because it's a finite space. We can't do any more than that. So what we can do, though, is we can add in, we can put more bits here, right? And, same kind of thing happening in 3-bit binary as in 2-bit binary, right? We roll over our values, right? We roll this 1 over to 0, which rolls, actually, we roll this 1 over to 0, which rolls the next 1 over to 0. And, right? And then we roll this over to 1 as well. Or this, however you want to think about it. And we can end up counting up to a representation of 7. So 7 in this case is 111. Something you might notice here is that in binary, if the first bit, if the rightmost bit is 0, then that's going to be an even number. 010 is 2, 100 is 4, 110 is 6. Whereas if we have the rightmost value as 1, that's going to be an odd number, and we'll see why that is momentarily. So here's 4-bit binary. In 4-bit binary, we can represent up to the decimal value 15 if we're going from 0 to 15. So now why is this? Why does binary correspond to decimal in this way? Let's consider this binary word 10110110. I would call this 8 bits, right? Because there's 8 bits. That's how we'll generally refer to that. So here's an 8-bit binary word. I'm using this term word, but you can think of it as just number, right? It's a binary number. It's a binary word. Word is how we usually talk about that when we're talking about binary. So we can break this down into place values in the same way that we would with decimal, where we've got a ones place, then a tens place, right? And then a hundreds place, then a thousands place. We can do the same thing with binary, except now we're talking about a ones place and a twos place, a fours place, an eights place, a 16s, 32s, and a 64s, and then a 128s if we're talking 8-bit binary. So the way that we can kind of math this out, the way we can translate this number into decimal is, well, if we've got this rightmost value of 0, then we take 0 times 1 because that's the ones place. The next value is 1. Well, this is 1 times 2 because that's the twos place. 4 times 1 because that's the fours place, and so on. And at the end of all this, we can just sum these numbers, right? If this first value is 128, well, we have at least a decimal value of, if this first value is 1 in 8-bit binary, then we have at least 128 in our resulting number. And then we don't add 64, then we do add 32, we do add 16, we don't add 0, and so on. And you can see that this corresponds to the zeros and ones in this number, right? It's almost like these are switches, right? And we do think about these like switches, where either, we turn on 128, we turn off 64, we turn on 32, and if we sum all those together, we get 182. And, thus we can translate pretty easily the binary number to a decimal value. So here's a question. What is the maximum decimal value that we can represent in 8-bit binary? And it might help to look at this up here. So if we had all ones, what's that maximum value that we can represent in 8-bit binary? It seems like it's 256, but yeah, 255 is the maximum decimal value we can represent. There's 256 potential values, but we have to include 0 as one of those values, right? So if we add 128 plus 64 plus 32 plus 16, right, all of those, we would get 255. So there's 256 total values, but we can represent up to 255. Okay. So I'm going to go ahead and code this out just so we can see it, because I'm going to be packing in a dictionary with this. Let's code a binary for a counter for 4-bit binary. And this is pretty easy. It looks a lot like what we've been doing at various times, and I'll do this in binomial. Okay, so if I define this as generate 4-bit binary, then I'm going to pack these into a dictionary where the keys in the dictionary are decimal values, and the values are the binary that would generate that decimal value. So I'm just going to make a dictionary here, and I'm just going to make a very simple counter for the decimal values. So here's this this thing again, where I have a bunch of nested loops, and I just change these for I, J, K, L, and at this point I can say, well, this bin dictionary DCT sub decimal is going to get a list. So our keys are integers and our values are lists in this case. So I, J, K, L. And then I want to increment decimal by 1. Decimal by 1. And at the end of all this, I'm just returning that binary dictionary. So if I get the decimal and binary out of this, it's just decimal. Oh, notice that bin, this is actually, it's a keyword in Python. So I'm going to do bin underscore in generate 4-bit binary. dot items. Dot items is how you get, that'll unpack into the decimal and bin values. That's how we do that. Then I can just print this f string of the decimal and the binary. And we should see, let's run this, Python binomial. Oh, binary dictionary is not defined because I called it DCT. Okay, so this is simply counting from, showing the representations of decimal and binary corresponding, right? So all zeros is 0, 0, 1, 0, 1 is 5. We can see this. We can see this relation. Just a quick note here. When we encode integers, it's actually slightly different from this, but not much, actually. Not much different from this. Because consider integers can be negative, and we need some way to encode negative numbers, which we're not doing here. We're just assuming all integers are positive, or all these relationships are positive. I'm not going to get into how to encode negative integers, but if you want to read more about it, ping me on it, and I'll point you at some articles. It is pretty cool if you're into how numbers are encoded on a kind of on a deeper level in the computer. Okay, so the question, a question to consider here is, how do we with these 4 bits, we can only encode up to the decimal value 15, right? Well, what if we wanted to count to arbitrarily high values in binary, in decimal? What if we wanted to represent arbitrarily high values in decimal? For example, the decimal value 1,436,272. How could we do that without this sort of without some massive amount of nested loops? Well, we're not going to do that with nested loops. That's not very practical, and it's pretty computationally expensive when you get down to it. So let's think about another way. We can use an algorithm to do this. There's a fairly simple algorithm. We usually call this dec to bin, and I'm going to have you code it in just a couple minutes. So it's a fairly simple process. We take a decimal number, we mod that number by 2, and we set aside the result of that mod. We floor divide the number by 2, and we keep doing this until that decimal number is 0. Then we look at our recording, which is it's just going to be ones and zeros, right? Because we're modding by 2. It's either going to be 0 or 1. We take that output and we reverse it. So I'm going to do this by hand to give you a sense of what this looks like, and then I'm going to have you code it. So let's do this with, the example I have is the number 43. So let's essentially do dec to bin of 43. All right, so why don't I get our algorithm in front of us, because I think it's nice to be able to look at that and kind of think about it as a set of rules that we're just following. Now, it's a little tiny down here, but well, maybe I'll make it a bit bigger. Yeah, there's probably enough space for that. Okay. All right, so we're starting with 43. And the first thing we do is we take the modulus by 2, right? So 43 mod 2. And the outcome of that is 1, right? Because it's an odd number, so we get 1. Now, the next thing we do is we set aside that result, then we floor divide 43 by 2. So 43 floor divided by 2, and I'm just using the Python version of that. This equals 21. So 43 floor divide 2 is 21. 21 mod 2, again, is going to be 1. And then 21, not mod, but floor divide 2, that's going to be 10, right? So that's 10. 10 mod 2 is going to be 0. And then 10 floor divide 2 is going to be 5. 5 mod 2 will be 1. And 5 floor divide 2 is going to be 2, right? 5 divided by 2 is 2.5, so the floor division of that is 2. So 2 mod 2 is 0, right? 2 goes into 2 evenly. And then 2 floor divided by 2 is going to be 1. 1 mod 2 is 1. And 1 floor divided by 2 is 0. Okay. So we take all of this and we reverse it. Do something wrong there? Oh, no. That's correct. Okay, good. What do I mean by reverse it? Well, we start at the bottom here, and we go up, right? So I'm going to say that 43 is going to be, for decimal, is going to be 101011 in binary. Okay, so that's the algorithm. And as you can see, we can do that algorithm by hand. It's a little time consuming, but we can do it. Now, what I'm going to have you do is code. This is that same example. And maybe what I'll do is put this on the side as reference. Remember to reverse at the end. And then you're going to code the decimal to binary function. So I'll make this this algorithm here just a little bit bigger so that it fits on the screen. And yeah, this is going to take it's going to have 2 parameters defined: the decimal number that you're putting in and the number of bits. Okay, so this is an interesting. This is part of the dilemma of it. If you want to have 8 bits, well, what is the 8-bit version of well, you can barely see it here, but this 101011 101011. Well, this is only 1, 2, 3, 4, 5, 6 bits. To make this 8 bits, we just pad the left with zeros. So that's the 8-bit representation of 43. Notice I'm just padding in 2 zeros. So think about that. If you can't get that to work, that's fine. I'm going to go through this either way. So I'll show you how to get it to be 8 bits or 16 bits, however much. Right, so those are your parameters, dec and n bits, and I'm gonna I'll put 6 minutes on this. So let me grab that, and yeah, feel free to get started. Give me a thumbs up if you want any more time on this. I can add a couple minutes. All right, let's go through a solution of this. And I'll keep this up here. All right, so maybe I'll give myself a little more space. There we go. So we're calling this deck to bin, and two parameters, the decimal value and some number of bits, which we're defaulting to 8. And I'm going to do this. I'll just make a collector bin list, and I'm going to make a copy of deck because I'm going to be modifying it. All right. So for whatever in the range number of bits. This is going to be how I solve that 0 padding, as we'll see. I can take the bit, and I can get the bit out of the modulus of x over 2, and then I can append I can append that bit, and then I can just floor divide x by 2. So that's it. And once x gets down to 0, well, x divided by, 0 divided by 2 is still 0. So this is going to continue to pad zeros. Remember, our list is reversed. And so at the end of this, I can return this. And one way I could return this is do list of reversed of the bin list. This is slightly less favorable than doing just bin list and then slicing it into a reversed form, like so. Okay, so let's call this deck to bin, and let's do deck to bin of 43, since that's the number that we were looking at by hand. And yeah, let's see if that worked. So 101011, right? That's 43, and then we've got 2 zeros of padding. So that's where we're starting in this exploration of binomial. Let's see where this goes. Okay. So we can collect these values into a dictionary, and I'll just show you how to do that. Oh, you know what? Let's take 6 minutes and just have a quick break. And when we come back, I'll start packing these values into a dictionary. Also, we're going to need this function later on, so I'm going to put it in the Slack. All right, I'll see y'all back here in 6 minutes. All right, so we can create a quick lookup table, right? And do that using a dictionary. This is sort of the, pack things into a dictionary and take a look at it phase of our analytic approach. So this is going to be pretty straightforward, I think. And let me know if this is confusing at all. So we're going to, I'm just going to call this get binary. I think that's what I called it before. And the number of bits that we're going to default to is 8. Okay. So if we're thinking of 8 bits, well, whatever number of bits that we are considering, we're going to go up to and include the potential representation of a decimal value in that number system, right? So we'll define a dictionary as bins d, and I'm going to say for dec in range, what should the range of this be for decimal values if we're considering 8 bits? Or what if this was 2 bits, right? What could we how many times would we want to call out to our dec to bin function? How many values could we call out if it was 2 bits? Yeah, we could go from 0 up to and including up to and including 3, right? Because 0, 0 is 0, 0, 1 is 1, 1, 0 is 2, 1, 1 is 3, right? And so the way that we want to think about this is 2 to the number of bits power. So if it was 8 bits, then the 2 to the 8 is going to be 256, and this is going to include every decimal value from 0 up to 255, because range is not inclusive. So that, let me know if that makes sense, why this is 2 to the n bits. Or let me know if that doesn't make sense, and we can jump back and look at it a little bit more. So that's how many times we're going to run this for loop. And then for every value in decimal, so bins d sub dec, we're going to call out to dec to bin and get the translation of that into binary. Of course, we're going to pack this in with binary lists. So dec, comma, n bits. So that's going to start at 0. Of course, that's going to be zeros, all zeros, a list of, let's say, length 8. That's all zeros. And then dec is going to be 1. And then we're going to pass in 1 and n bits, which is 8. And we're going to get 0, 0, 0, 0, 0, 0, 0, 1, right? And then we're going to keep doing that. We're going to keep getting values out of this. So we can return bins d. And to see these results, I'll just do this for dec bin in get binary. Number of bits, let's just do 8. And I'll print the f string dec and bin. So let's take a look at that. Oh, bin is not defined. Oh. Okay, let's try that again. And here's the binary representation for every value between 0 and 255, as we can see there. All right. So that's all well and good. We can count in binary, but the question really here is why binary? Why binary? The reason why binary is that we can think of a binary number as being a binomial process and representing outcomes of failures and successes. So the binary number 1100, we can think of like 4 coin flips where we got heads, heads, tails, tails, right? We can think about it that way. And through this binary counting process, we have created an exhaustive sample space for the number of successes in n trials, which is essentially the definition of binomial. So yeah, the count of ones in 4-bit binary will follow a binomial distribution with a probability of 0.5 per trial. And we can see that like this. These are the counts of the sums of ones for 4-bit binary. So there 0, all zeros, occurs 1 time. 4, which is all ones, occurs 1 time. And then 1, which is some arrangement of 1 across 4 zeros, right? 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, or 1, 0, 0, 0. Those are the 4 different ways that we can arrange to find 1. And similarly, 2, there are 6 different ways to spread 2 across 4 bits. Okay. Notice that with a probability of 0.5, as we have, our modal value, our expectation here, is going to be this middle value. If we had 0, 1, 2, 3, 4, 5, then 2 and 3 would actually have equal counts, and they would both be our modal values, and 2.5 would be our expectation. Of course, we can't get 2.5. We're either going to get a 2 or a 3, but 2.5 becomes our expectation. So that gives a sense here of what our expectation is from a binomial distribution with probability 0.5. Well, it's 0.5 times the number of Bernoulli trials. That would be our expectation. So for 12 Bernoulli trials, our expectation would be 6 with a probability of 0.5. And what if our probability changes? It turns out, and we'll see this in a bit, if our probability is 0.25, well, the expectation in 12 trials would be 3. So, that's a quarter of 12. So that's something that is observable in this process. All right. So we can construct, we've already sort of done this. If you think about it, we've already constructed binomial for n trials with a probability of 0.5. But let's take this a little further, right? So in our binary approach, we're stuck with this probability per trial of 0.5. At least currently we are. We're going to do something about that a little bit later. But yeah, let's build a binomial distribution with this approach. So there we go. So I'll start coding this, and I'll talk us through it as we go. So again, this is using a counting approach. And if we think of the binomial distribution as representing the sum of ones in a binomial word, or the number of successes in a series of Bernoulli trials, we can think of those two concepts as being equivalent, as I said. So let's just traverse a set of possibilities for 8 Bernoulli trials. And this is just going to be kind of an adaptation of our last function. I'm going to call it binomial distribution for some number of trials, and I'll set this to 8. And I can, I'm going to call this binomial dictionary. And the first thing I'm going to do is I'm actually just going to get a binary dictionary from our previous function. So from get binary, where the number of bits equals the number of trials, right? So we're making I'm making a clear statement here that bits and trials are equivalent. And then all we have to do is traverse this binary dictionary, bin dict, yep, dot items. I don't need that decimal value, so I'm just putting an underscore here. Oops, underscore comma. And, we're just disposing of that. We're not collecting the decimal values. The translation between decimal and binary is not entirely relevant here, except for the building of the sample space. Okay, so the sum of the bits, that's what we're looking for, right? 1, 0, 1, 1, 0, 1, 0, 0 would have a sum of bits of 4, right? There's 4 ones in there. So that's what we're looking for. So how do we build that? Well, we can say the sum of the bits just gets the sum of val, right? We can just sum that binary list, and that gets us the number of successes. And then if that sum of the bits is not already in the binomial dictionary, this is a pattern that we're going to see. If it's not in there, then I'm going to put it in there. Binomial dictionary sub sum of the bits is going to, I do this, as I said before, I initialize it to 0, then I increment it by 1, and that's it. That should get us, that should get us a binomial distribution, or a distribution of counts in binomial is what we're going to see here, actually. We're not going to see, in this case, we're not going to see the frequency of occurrences. We're going to see the count of occurrences that we would expect for 8 trials, for example. I'm going to do this for 12 trials. So let's see what that looks like. I'm going to call out to binomial distribution. I'm going to set the number of trials to 12. And then, so for the counts, we can do this for k, v, in d.items. And I'll print an f string of the key value, the keys and the values, that is. So key and v. So k, it's interesting here because k, even though we mean key, we also mean the value k in the binomial distribution. When we get to the actual closed formula for the binomial distribution, we still call this k. As it turns out, we call it k. Because we're asking the question, what is the probability of k occurrences in n trials given a probability of something, of 0.5 in this case. Okay, so this will give us the counts, and then let's see. So here are the counts, and I'll blow this up a little bit. So we can see clearly that our expectation is 6, right? That's 0.5 times 12. We've got 12 trials. We have an expectation of 6. We can see that this is symmetrical, right? We've got 792, then 495, 220, 66, 12, 1. This is a binomial distribution where our probability is 0.5 and the number of trials is 12. So I want you to maybe give me a code snippet that instead of providing me counts, instead of providing me the counts, provides me the probability of each value of k. So I'm not going to put a time constraint on that. Just how would you adapt these lines 63 and 64, to provide me the probability of different values of k? And as soon as you get to a quick answer on that, just go ahead and put it in the Slack. And just in case you need it, I put this entire code, all the code for this part of it, into the Slack. Okay, so seems like maybe this has y'all stumped just a little bit. We can do a traversal of the items in the dictionary. And if I want to output the probabilities, well, the probability of any given outcome, right, the probability of k, is going to be, if we look at it here, like the probability of 8 is going to be 8 divided by, well, everything, right? 8 divided by, 495, which is the number of times 8 successes occurs over 12 trials in our counting approach. It's going to be 495 divided by the sum of all those values. And in Python, the way we can do that, well, we can say d.values, right? So it's going to be the value divided by d.values, except d.values is a list, or a list-like object. We can just take the sum of those. And so if we do that, we can start answering questions of probability. So let me go ahead and run that. And now we're looking at probabilities. The probability of getting 6 successes in 12 trials with a, where the probability of any given trial is 0.5. Well, that's going to be 0.225 or 0.226, 0.2256, whatever precision we're going to consider there. So I'll put that in the Slack as well, because I think the next question is going to call for that. So let me make this fit on the screen a little bit better. Oh, still doesn't fit. Let's try that again. Okay. So you've got this code in the Slack. Feel free to copy paste it. It's going to be helpful in answering this question. You flip a coin 12 times. So the way we think about this is n is the number of Bernoulli trials. K is the number of successes that we're looking for the probability of, right? P is the probability of success on any given trial. So what is the probability that you get 9 heads in 12 flips? And just let me know what are the values of n, k, and p. And then what is the probability that you get 9 heads? Shoot. That was supposed to be a different number. Let's just answer this one. What is the probability that you get 9 heads in 12 flips? And this says 4 minutes. Let's do 2 minutes. So all you really need to do is run this code and look it up in the table. And when you get to an answer, feel free to post it in the Slack. Okay, so looks like everyone's getting to that right answer, 0.05371, right? However we want to round that. So the second part of the question I actually have here. The other part that our value of n, right? N is 12. N is 12. That's 12 trials. Our value of k is 9, right? That's what we're the probability we're looking for is the probability of 9 heads, and or 9 successes, however you want to think about that. And our probability is 0.5. Our p is 0.5. Okay, so here's the second part of that, and let's just take another 2 minutes to answer this. What is the probability that you... Oh, that's the same exact thing. Sorry. Let me get you the question I'm actually asking, which I have in front of me down here. Okay. What is the probability of getting 4 or less heads in 12 flips? So let's put 2 minutes on the clock for that. And give me how you came to that conclusion, as well as the probability. My apologies. I am just going back and finding where that slide was. Haha, there it is. Okay. So the way that we can think about this is the probability that x is 0 plus x being 1 plus x being 2 plus x being 3 and so on. And that's really, it's really just a summation of those, right? And it looks like that's 0.19384. The way that I might do that in Python, well, that would be easy enough to do, I think, if we just did, for example, d sub 0 plus d sub 1 plus d sub 2 plus d sub 3. So it's going to be that divided by the sum of d sub d, the sum of d sub dot values, right? So this would be, you know, the probability of getting d sub 3 plus d sub 4, actually, of getting 4 or less heads in 12 fair coin flips. Okay. All right, so that's kind of our tour of counting for binomial, counting in binary. We're going to switch gears and look at this from a sampling perspective. So understanding the binomial distribution through sampling. We can have some other flexibilities in sampling. You know, the flexibility of having an arbitrary length list is still there, and we are going to be able to approach having a variable p, a variable probability with sampling. So we're going to construct binomial first with a fixed value for a fixed probability for each Bernoulli trial. So let's call this binomial through sampling. And I'm going to use the choice function here from the random library. So from random, import choice. Normally we would put this at the top of the file, so I'm going to do that. We also are importing random somewhere later. I don't think we imported it yet. Let me just make sure. Nope. Okay, good. All right. So the way we can do this, I'm just going to do it in 2 steps. I'm going to first get a bit, either just a 0 or 1, and that's where I'm going to utilize choice. So I'll just return the choice from 0 or 1. Maybe I'll make that a little bit bigger. Okay, now we want to be able to generate n bits. That's easy given this function, although we don't really need a helper function here. I think it's nice to have one. This is kind of like a Bernoulli trial with probability of a probability of 0.5, right? So let's generate n bits, and I'll default n to 8, and we'll just return. Well, I'll write this longhand first. So if we're going to take a collector approach, accumulator collector approach, we'll instantiate the list, then we'll say for whatever in range n, we'll append bits to that list. And then we can return the list. So this will work. I'll just call it really quick. So print generate n bits, and let's generate 12 bits. Oh, I didn't save it, and I'm still outputting this. So let's go ahead and do that. Okay, so let's take a look at that again. And here we've got some binary outcome. Now, if I run this again, of course, we're going to get something different. And I can keep running this, and we'll keep getting different binary lists. I'm going to rewrite this to be a comprehension. It's one of those kind of ideal situations for comprehension. So I'm going to get a bit for every value, or for every iteration in a range, for whatever in range, the range of n. So that's just a little like short one-liner, two-liner, right? And that'll work in exactly the same way. Okay. So we have that. The next thing you're going to do, and in fact, you're going to need this. So why don't I go ahead and paste this into the Slack. what you're going to do is you're going to write a function called binary sampling dictionary. And this is going to take two parameters, the number of bits and a number of samples. And what you're going to do is you're going to call out to that generate n bits num samples times. You're going to count the number of bits, right? And let's say you get 8 bits, let's say 8 ones. You're going to add the key for 8 into the dictionary, and then you're going to increment the value for that key by 1. So basically what you're doing is essentially what I did just a little bit ago, except instead of counting, we're sampling out and populating a dictionary. So it's going to be a slightly different process. Right, so your data structure will look something like this. 0 has to be in there. Well, it doesn't have to be. If you never get 0, then you never get 0 through your sampling process. But if you do get 0, you're going to add that as a key. And every time you get 0, you're going to increment the counter in relation to that key. And you're going to go up to the number of bits times. So remember, right, if we draw 0, 0, 1, 0, 1, 1, 0, 1, that's 4 successes, right? So that would, you would create or increment the key 4 by 1. Okay. If you have any questions on this, please ask. And otherwise, I'm going to set 4 minutes. Let's do 5 minutes. And you're going to write binary sampling dictionary according to this description. Give me a thumbs up if you need any more time on this one. All right, I'm going to take us through a solution. Yeah, let's do it. Okay. So in our sort of common sampling approach, we're going to have some number of samples, right? So I'm going to call this binary sampling dictionary, and we're going to have a number of bits, which I think I set to 8 by default, and then a number of samples, which I set to 1,000 by default. Okay. And then, we just create a dictionary, and we're going to collect outcomes into this dictionary for whatever in range the number of samples. So we're going to do this num samples times. I'm going to get some binary, and I'm going to get that from generate n bits. And that's going to be of the length number of bits. So I'm going to just put this into a couple operations. I could have just done this in one line, but I'm going to say we have an observed k, right? Our observed sum of ones in the binary number. That's just going to be the sum of the binary. If that observed k is not in the dictionary, then I put it into the dictionary, right? D sub observed k. Is going to get initialized to 0, and then, and then I increment it. Okay, let's fix that. I increment it by 1. And when all that's said and done, I can return the dictionary, and I should be able to see some result here, okay? I think we have time for one more breakout, but let's observe the result of this. I'm going to do one trial of 1,000 samples, and I'll just make this dictionary D. This is going to be binary sampling dictionary. We'll do 8. I think that's easy. And I'll say for key and value in the sorted d.items. I'm sorting this because I don't know which value of k we added first, and I can't guarantee. I just want to see them in order. I want to go from 0 up until 8. So let's print the f string of this, k v, and I think that should work. All right. So if I look at this, it's not symmetrical, but we wouldn't expect it to be, right? At this point, we wouldn't expect this to be symmetrical because this is just one trial of 1,000 samples. And so we're going to see a lot of variability here. This isn't, we're not going to see something that perfectly resembles the theoretical distribution, the distribution that we constructed either by counting or potentially we can construct using the PMF when we get there. What we do have here is something that looks fairly binomial, right? We've got our expectation here at 4. That makes sense. Or our modal value, I should say, at 4. That makes sense. We don't have a perfect symmetry around this, but maybe we have a relative symmetry. And if we ran this more times, we could see that. You know, we maybe if we run this enough times, we'll actually perfectly get a binomial distribution as if we were counting. It might be a fun game to, see how many trials it takes before we do that, right? How many times do we call this before we actually get a perfect representation of a binomial distribution? That would actually lead us into having a geometric distribution, right? The number of failures up until the first success. And then we could analyze, this is just, thinking about things you could play around with. You could analyze, depending on the number of trials, how many times on average it takes to achieve something that looks binomial or is perfectly binomial according to what we see when we're counting. That's something you could do. You could play around with that. That would probably be another distribution. It would be a comparison of distributions of it would be a comparison of various geometric distributions, and we could come up with some average, right? These are the kinds of things that we start thinking about when we're in this material. What can you do to gain surety? How do you think about a problem like this? Like we're sampling, but what kind of random process is even involved in sampling? So let's take a peek at the next challenge, but let's not do it. I just want you to think about it, and we'll pick it up from here on Saturday. On Thursday. We'll pick this up tomorrow. We've got this breakout, not this breakout, but the next one, where I'm going to have you run some code. I'm going to have you run code for 16 bits, getting a dictionary for 16 bits and outputting the probabilities. So the probabilities relative to that sample, or for that trial of 100 samples, and then the probabilities relative to the trial of 1,000 samples. So the thing that I'm going to ask for here is a description of what these differences, what the difference between these two represents. And that's going to be relative to the number of samples taken for that trial. But yeah, let's call it there, and we'll pick up at this breakout. We'll probably review the code here first, and then we'll pick up at this breakout tomorrow. So yeah, that's the lecture for today. If you have any questions, stay on. Let me stop recording really quick, and feel free to come on.